Hi, hello everyone. My name is Paula. While I present myself and introduce the speakers we have with me, I have with me today, can you let me know in the chat if you can hear me and if you can see us all well? So super quick, my name is Paula. I work at Ironhack in the marketing department, and well, I mostly do community and events, so maybe you know me from other webinars. Let me know also in the chat where are you seeing the webinar from, and if you have attended previous webinars or if this is the first one, okay? So with us today, I have Paolo and Erin. These special speakers today, they're going to be introducing you to decision trees and machine learning. So it's going to be an interesting topic. It's the first one it's the first time we actually do a webinar in machine learning. So I'm really thrilled to see how it goes and if you like it. So a little bit about Ironhack and what we do. We are a tech school and we do bootcamps or part-time courses in web development, data analytics, cybersecurity, and UX UI design. And we have campuses in 9 cities around the world. And actually, Paulo teaches at Amsterdam, and Erin usually also teaches at Amsterdam, but she's right now teaching in Berlin for some time, but she'll be back to Amsterdam at the end of the month. So myself, for example, I'm based in Barcelona, and I also studied data analytics last year in Barcelona. So all good to see that you're seeing us from everywhere in the world. Super quick before we start with the introductions, how to use Crowdcast and how to see the webinar. If you have any questions, if you get lost at the middle of the presentation, you can always ask a question in the Ask a Question down below. Please put every question you have there, because if you type it in the chat, maybe we don't see it, it gets lost. So just put it in the Ask a Question and we'll address it at some point, okay? What else? If you get lost, don't worry. Embrace the moment, try to learn as much as you can. We are going to send you the recording of the webinar after it finishes, so you can see it as much as you want. You can review the concepts and maybe get it from the point that you got lost. So don't worry about it. Just try to have as much fun as possible. And yeah, I'm just going to let Paolo and Erin introduce themselves, and maybe we can start with the class.
Yes, thank you. Thank you, Paula. I'm Paolo Scalia, and I am teaching assistant for the data analytics course in Amsterdam, the part-time version. And the course is actually about to start in a week. So if you're interested, if you like the webinar, or if you're interested in data analytics, there is still time to register. And I would like before we start, I would like to ask Erin also to introduce herself.
Yeah, hello, I'm Erin Berardi. I'm currently a teacher's assistant for the full-time data analytics course in Berlin. Although I live in Amsterdam, we've been here about 4 years now. I'm originally from the United States, moved to Amsterdam with my husband as an expat for his work, and decided to completely change my career. I guess it's not completely changed. I took the data analytics boot camp almost a year ago now, and I was originally a middle school math teacher. So different for me, but now as a TA, I feel kind of back more in my element again.
Thank you, Erin. I think we can start. So Erin will be supporting us with answering some of the questions and pointing issues out to me and to Paula. I would like to start by sharing the screen. Let me start one. A moment. Yes. Can you see my screen, my slide?
Not just yet, but let's wait because I think it might get. Okay, well, I think we'll wait for Paolo to come back. It's cool to see that you're seeing us from all over the world. And yeah, Erin, they are talking about your impressive transition from middle school teacher to to data analytics master. It's really cool.
Yeah, it was a very big change out of my comfort zone entirely. But the Ironhack was fabulous. The boot camp was great.
And
very supportive.
What made you took the bootcamp? Like, why did you want to study data analytics?
Well, I had a conversation with my husband about the fact that I'm trained as a teacher, and that's all I've done. Been a teacher for 25 years. Mm-hmm. And I said, I have no other skills. That's what I do. That's what I am. And he said, okay, so in your teaching, what's the least teachery thing you did? And that was explaining standardized test results to the parents, which is, it's a sheet of paper with percentiles and lots of statistics and how did their kid do compared to everyone else. And when I mentioned that to him, actually, he said, maybe you should look into data analytics.
That's right.
And yeah, so it was like, that was the one thing that I really enjoyed that wasn't really teaching for me.
Yeah.
So
that's really good.
Hi, Paolo.
Hi.
Sorry, with some issues, some technical issues. Let me try again to share the screen.
For everyone in the chat, we tested everything right before it started, and it worked great. So it's just like the live problems.
Yes. Okay, can you see my screen?
Not yet. Can you get the message from broadcast that you're sharing the screen?
Yes. Maybe it will take a second.
Yep.
Still nothing?
Now we can see it. Yep.
Okay, perfect.
Yes, now I can see it.
Cool.
Thank you.
No worries.
So good. Let's start then. So good evening, everyone. Again, sorry for the interruption. So today, I would like to introduce you to one of the most well-known and used machine learning algorithms. And I would like to use this beautiful picture here to lead us into the topic. This is, as you can see, a huge tree surrounded by normal trees. It's in California, and it's one of the tallest trees in the world. It's called the Mendocino, and it is over 110 meters tall. So it's a gigantic tree, and it's perfect to lead us into today's topic, which is, as you already know, decision trees. Let's start with seeing what's on the menu today. I will start with some definitions and review of important concepts. Then I will introduce the tree algorithm, which is the core of the presentation. A couple of examples to show how this algorithm, the tree algorithm, is used in real life and how it's being used and is currently used. Then I will give you overview of the advantages and limitations of the algorithm, how we could solve these limitations going beyond single trees, the conclusions, and then a small demo. And I will take a few minutes. We will take a few minutes break in between the conclusions and the demo, so that we can reflect on the presentation and on the concepts presented before going into the demo. So decision trees are versatile algorithms for regression and classification problems. This is the classical definition, and but there are three words here that are quite interesting, and we should deconstruct them. The first one is algorithm, and I would like to ask you, and you can answer me in the chat, what do you think could be a definition of algorithm? What do you think could be defined as algorithm? Let me know in the chat. I will wait for your answer. Any ideas? Oh, Ronald says set of rules, series of steps to solve a problem. Exactly. So this is a very, you're all answering correctly. So this is exactly the definition of algorithm. So in fact, algorithm is a set of instructions to complete a task, as some of you pointed out. And just to give you an example, I want to present you the coffee algorithm to make coffee, Italian coffee in particular, because I'm Italian. I enjoy my coffee. You see, this is the external part of the mocha machine, the Italian machine, but it's more complex. If you open it and if you unmount it, unscrew it, and you look inside, you will see a series of components, and the series of components can be coupled to this coffee algorithm, which is the algorithm to make coffee. And for example, first of all, we go and fill the water vessel with water, then mount the funnel on the vessel. We pour the ground coffee in the funnel, which is this one here. Then mount the coffee collector, where actually once the coffee is ready, that will be collected here on top. Then place the mocha on the stove and wait impatiently for the coffee to brew, and then serve the coffee. So this is, for example, an algorithm that could work to make coffee. And I would like to ask you at this point, could you give me just a quick example, maybe in the chat, of an algorithm that you might think of? In fact, an algorithm is you can see it also as a recipe. As a recipe when you look up a recipe to make dinner, to make lunch, the set of instructions that you're presented with, that is an algorithm. So this was the first word, algorithm, which we are now deconstructing. We deconstructed. And the second question is, what are regression and classification problems? So these two words here also, you can see them everywhere in machine learning, and many problems are regressive problems, and many other problems are classification problems. Let's give an example of a regression and a classification problem. A regression problem is something that usually answers the question, for example, what is the temperature going to be tomorrow? We are looking for the specific temperature, for example, 84 degrees Fahrenheit. So it's a precise answer. It's a single number. where a classification problem answers a completely different question. In this example, will it be cold or hot tomorrow? So we'll be happy with knowing whether the temperature will be, for example, between -infinity and 10 degrees Celsius, if we define cold as within this bracket, and hot between 10 degrees Celsius and +infinity, for example. So we're not interested in knowing the exact number, but just a qualitative answer. I hope this is clear, because it's an important concept. And I would like you also to share with me a couple of examples in the chat of regression and classification problems that you might think of. And Jesse, I like your example, the algorithm to make a toast. That is also a delicious one. So we can have coffee and make a toast. So let me know if you can think of interesting regression or classification problems in the chat. And today we'll be focusing on classification problems for the tree algorithm. A similar story holds for regression, but we will focus our attention on classification. So we deconstructed these three important words: algorithm, regression, and classification. And now, what can we do with an algorithm? So we can use the algorithm and data to create a model, and the model makes a prediction. It's a recipe to make a prediction. And the important concepts that I would like you to focus on here and to remember is that, so the algorithm, as you also pointed out, is a set of rules, but it cannot do anything on its own. It needs the data. Same way as, to make coffee, you need the machine, but it's not enough. You need coffee. You need ground coffee to make coffee. And in this analogy, data is your ground coffee. So if you the same way as you use the machine and ground coffee to make an espresso, you let the algorithm run on part of your data to create the model, and that is called also the training phase. And the model is, in other words, is a recipe to make a prediction, but is combined of these two ingredients: the algorithm and some of the data. So after we created the model using the algorithm and part of the data, and we will see an example, then the next step is testing the performance of the model. As you can see here in the pictures, it is always an exciting part, because sometimes it happens that the training phase goes very well. So you see that the prediction made by the model in the training phase are very accurate, but then when you test it on new data that the algorithm has not used to make the model, then it fails miserably. So it's always exciting to to test a model. And now let's try to see a practical example. Like I said, we'll focus our attention on a classification problem. And the classification problem that I would like to present here is the problem of a teacher that wants to predict whether his or her students are going to pass or fail the exam at the end of the course based on a series of data. And in this example, the data are shown here in this table that you see on the right part of the slide. For example, the number of hours that the student could study to complete the course, the percentage of lessons that the student could follow the course, and the percentage of times that the student was late. This could also have an impact on whether the student will pass or fail the exam at the end of the course. And just to get more comfortable with the machine learning terms or words, so these variables, so the hours, the percentage of lessons, the percentage of time that the students was late, these are all the ingredients that we will use to make the prediction, whether the prediction meaning whether the students will pass or fail. These are called the features, and the response is whether the students will pass or fail. This is also something that response or target. This is something which is these words are used quite often, meaning the quantity that we want to predict. And like I said, a part of the data will be used to train the model. So the algorithm will use the part of the data to make the model. Then the model will be tested with new data which have not been used in the training phase. And then once this is completed, we can unleash our model in the wild, and asking the model to predict something that we don't know. Well, in this case, in the test phase, we know the answer. So we know the answer, but we don't tell the algorithm. We let the algorithm guess the answers, and then we can check whether the algorithm was right or wrong. So we can really test if the training part worked. Well, in the predict phase, in predict part, we don't know the answer ourselves, so we just have to trust the algorithm. Up to now, so I haven't said anything about decision trees or anything specific to the decision tree algorithm. This is up to now is what I've said is general to machine learning, to any algorithm. Now let's go into the specifics of the classification tree algorithm. So how does the classification tree, the algorithm, approaches this problem? So how does it try to predict whether the students will pass or fail? Essentially through a series of yes and no questions. And the series of yes and no questions will be shown in a flowchart like this one here. This is an example of a decision tree. And you see the decision tree takes some of the variables, or all of the variables, in this case, the number of hours, the lessons, the percentage of time it was late, and decides a certain number of splits, meaning specific values for the features, which are critical to decide whether the students will pass or fail. So if we had to read this flowchart from top to bottom, it will go like this. So if the number of hours is less than 15, the student will fail. Otherwise, if the number of hours is more than 15, this is not enough. Then we'll have to look at whether the percentage of lessons is less than 60. If yes, the students will fail. If not, then we look at whether the student was late. If it's according to the model made by the algorithm and the data, if the student is late less than 30% of the time, will pass. Otherwise, it will fail. So, and this is the decision tree style. So using the features and finding these critical splits that will help answer these questions and classify the students according to whether we fail or pass. And now there is also an interesting question. What is the relationship between this flowchart, for example, and a tree, a real tree, I mean? Do you have an idea? Let me know if you have an idea. So what do you think is the relationship between between this flowchart and the real tree. Branches, I see branches. Yes, it gets smaller at the end. Carla, yes. Yes, it gets smaller at the end. And this is all true. And moreover, there is one other thing. So the relationship is with an upside down tree. So you see the main root corresponds to the first feature. The green part here, this segments here are the branches of the tree. These internal parts are where lessons are later the internal nodes of the tree. And then the values of the response, so fail and pass, are the leaves of the tree. And so this is a bit maybe counterintuitive relationship between the tree and the real tree and the algorithm. It's with an upside down tree. But now let's go a little, let's go one level deeper. So this is an example, I showed here as an example of a possible tree, but the question that we have here now going deeper is how does the algorithm chooses the features and the splits? Why 15, why 60, why 30, and how does it choose? It doesn't need to choose all the features. So what's the process? Let's start with smaller examples where we have 10 students and 10 students fail and 10 students pass. How do we build the algorithm? So how does the algorithm, what is the set of rules that the algorithm follows to build the tree, starting from this situation? Well, the algorithm starts with a single feature, and then it will split it to maximize the purity of the leaves. So in other words, if we look at this two-dimensional representation, which is easier in this case, we are looking only at two of the features. It means that the algorithm will try to split, this space with vertical and horizontal lines, trying to create regions which are red or green as much as possible. So it tries to make order out of the disorder that we have at the beginning. So here at the beginning, we have a disordered area, which is 50% fail and 50% pass. And the algorithm tries to create these divisions to create ordered areas within the space. For example, in this case, it creates two regions, and they are not perfect, you see, but this one on the left that corresponds to pass as majority of green, so it means that most of the time it is correct, and here on the right it's mostly red, so fail, and it's mostly correct. It's not perfect, but it's the best that the algorithm can do. And this is how it creates the first split. So, and we go, you see, from a lot of disorder, because here we have 50% fail and 50% pass. And these two areas that the algorithm creates are more ordered than the initial regions. So, and this is how the algorithm proceeds. It tries to keep building. We see another iteration here, keeps building these divisions with vertical and horizontal lines till a stopping criterion is met. For example, till there are maybe less than 5 points in each, or more than less than up to 5 points in each region. And so it will keep on going. If there is no stopping criterion, it will keep on going, subdividing till it has maximum order, meaning again regions which are as much as possible green or red. And this was an example in 2 dimensions with 2 features, but it can be generalized in many more dimensions, but it's more difficult to see. And this is how you see the combination of the training data plus the algorithm, the set of rules, created a model. So this is the model, essentially, that we can use to test the algorithm. So we know that if a student studied less than 15 hours, then it will pass. Otherwise, if he studied more than 15 hours, but it attended less than 60% of the lessons, it will fail. Otherwise, it will pass. This is the model that the algorithm with the training data was able to build, creating these ordered areas as much as possible. And now we can use the other part of the data, so this other part of the data to test the algorithm. So in this example, you see these are new data, which have not been used by the algorithm to make the model. And you will see that here it's quite the test is quite good, because the new data, the student that passed goes into the region predicted by the model to pass. There are some errors, but this is normal. And here fail. The new data go into the more or less into the right region. So now we are happy, for example, with this model and with the test, and we could, if we wanted, unleash the algorithm in the wild and ask the algorithm to predict on students, on new students for which we don't have, the values of the response, and then we'll have to trust the algorithm. And this is, well, up to here, I tried. So this is the most important part of this webinar. So the main words used in machine learning that we've seen. So algorithm, classification, regression. The idea behind the decision tree that tries to order the space, to organize the space in homogeneous areas. So mostly green or mostly red in this example, tries to find the features and the values of the splits that make this space as much ordered as possible. And here we could, if we don't have a stopping phase, the algorithm could go forever. So until every single data point is classified. You see, and it will be perfect. So it will find a perfect, maybe regions for each data point, and it will be correct. So it will have a perfect performance on the training data. So it will have a perfect classification. And what do you think here? Is this real, or do you think this performance is real? Having perfect performance on training data, would you be happy with that? And if not, why not? I mean, if you have some ideas about it, just let me know in the chat. So can we have perfect performance? Exactly. So I see Zinnia. Yes, I agree with you. If you introduce new data, it will be confused. Yes. So the perfect performance on the training data is possible, but we all know that perfection doesn't exist. Nobody's perfect, and not even the algorithm. So perfect performance on the training data is an illusion. Perfection is an illusion, because if we then use new data, so if we test the algorithm with new data, we will see that it will fail it will fail miserably. So because these areas are too small, so these regions are too confined, the algorithm will not be able to generalize well to data which have not been seen by the algorithm. So the perfect performance on training data with all these small regions, it will most of the time result in a very poor performance on the test data. So the test phase will be not successful. This is one of the situations where you have good performance on training and bad performance on testing. But you can catch it. You will see. And of course, the performance on the test is really what counts, because you're testing the model on data which have not been used to make the model. So the training data are used by the algorithm to make the model. So you might expect that the algorithm, that the model is successful at classifying the students, because you use those data to make the model. But once the model is made, just the proof of fire is when you feed the algorithm, you feed the model with data which have not been seen. And in these situations where you allow the tree to grow very deep, meaning that it will have many nodes, then it will fail. So I hope this part was clear. Now I would like to give you a couple of examples of where this decision tree algorithm can be employed and how it can be successful. My favorite example is when trees can save lives. And this example was taken from an interesting read. I advise you to read it if you're interested in this type of books. It's called The Power of Thinking Without Thinking by Malcolm Gladwell. And in this book, one of the chapters focuses on one of the early adoptions of decision trees in healthcare, where there was this county hospital, Cook County Hospital in the States, which was understaffed and was flooded with a lot of patients. We were having cardiac problems, or they thought we were having heart attacks, but diagnosing heart attack is not that easy. So to play it safe, they were sending everyone to the high-risk units, flooding the high-risk units with so many patients that they were not able to handle them and to treat the patients that were actually needing to be in the high-risk unit. So one of the managers, based on some of the early papers on decision trees, and with some collaborators, put in place this flowchart, this scheme, where the patients are streamlined into the high-risk units, or moderate risk, or low risk, or very low risk units, according to this scheme. So if there is acute evidence of myocardial infarction, then we go to high risk. The patient is streamlined to high risk. If not, Again, it goes one level deeper, and we ask for evidence of acute ischemia. If yes, we look for urgent factors. For example, if the patient is diabetic or is overweight. If yes, again, high risk. If not, moderate risk. And again, if there's no if there's no evidence of acute ischemia, we again look at urgent factors, and we streamlined according whether the urgent factors are present or not into low risk or high risk units. And this is, I think, a beautiful example of how these models can be employed in real life and simplify healthcare. Another more mundane example is in banking. So trees can prevent fraud in the following sense. So we can use a number of features. For example, the amount of the transaction, the times of transaction in the last day, the transaction time, to determine whether the transaction is fraudulent or not fraudulent. In real life, these trees are bigger or deeper, but I thought here I would give you an example of some of the important features that are used to make these predictions. So, and nowadays they're still used. Like I said, they're more complex, but the idea behind it still holds. And these were the two examples. So, and now I would like to just pause one moment and think about the advantages and disadvantages of the trees that we have seen so far. So there are many advantages. One of the main advantages, as we have seen, is that they're easy to visualize. So this flowchart structure is easy to interpret. And this is something important because it helps to build trust in the model, especially from non-technical colleagues, non-technical shareholders. If you take, for example, a much more complex algorithm, deep learning, for example, neural network, then it might be more performing than a decision tree, but it's much more difficult to explain. While the decision tree, the output of the decision tree is a flowchart that you can show to everyone, and the threshold to interpret it, to understand, is much lower. And then it's easy to transform in business rules. So the business logics can be clear. The decisions that the tree makes can be implemented directly, following the flowchart. And it's very eclectic in the sense that it can handle many types of relationships between the data. If you take another algorithm, for example, a linear regression, the linear regression algorithm works very well if there is a linear relationship between the data, simple relationship between the variables. The tree doesn't need that. So it works well with very complex relationships with the data. But as we have seen, it is prone to overfitting, meaning the problem that we just discussed. So if we don't do anything to the tree, if we let it grow very deep, then it will perform very well on the training part, perfect performance there, but it will be a disaster on the test phase. And this is called also overfitting, because it's fitting too well the training data. It's memorizing too well the training data that it doesn't know how to deal with new data, because it doesn't know how to generalize to new data. And the prediction performance can be improved. So it is an algorithm where the interpretability is, use it when the interpretability is more important than the performance. There are algorithms that can solve classification or regression problems more accurately. For example, maybe deep learning or neural networks or logistic regressions or other algorithms, but they're not as easy to explain to other people. So there's always a trade-off. Now I just want to say a few words on how we can improve the prediction performance of the trees. But this is not the most important part, but some of you might be interested. And the main idea is to bring together many trees. So to make a forest out of a tree. So a tree on its own is also known as a weak learner because it, like we've seen, it doesn't predict very well, it can be overfitting. But if we put together many trees, the prediction performance can improve considerably. So what you do is you start with the original data set, and there are ways to create, slightly different data sets from the original one. And then you create a tree for each of this data set that all come from the original data set, and then you average the result of these multiple trees, and this counters the variance, counters the overfitting that we've seen earlier on. But there is a problem. So here the performance is improved, but the interpretability goes down, because here we are talking about usually you average 100, 1,000, 10,000 trees in this procedure called bagging. And then how do you show to someone else the result of 10,000 trees? It's much more difficult. So you lose interpretability, but you gain in performance. And this is another step into improving the performance, where you maximize. So it's the same approach as bagging that we've seen here, but you try to average trees which are very different from one another. So the details are not important at this point, but you keep averaging to improve the performance, but you create trees which are different from one another. And you can show that this works very well. So diversity is something that works very well also in machine learning. And this brings me to my conclusions. So I hope I convinced you that decision trees are versatile models, that they privilege explainability over predictability. So this is something not to underestimate, I think. They're ideal to handle business logics in a transparent way, because you can quickly explain or easily explain via a flowchart the decisions made by the algorithm to your colleagues, to non-technical colleagues, to stakeholders, to managers, and that helps build trust in the model. You gain the possibility that your model is used in production, that is implemented. More complex models, which are maybe more successful, who have more predictive power, they are not as good as building trust in the company, in the teams, because they're black boxes. They're more difficult to understand how they work and why they made the decisions that they make. And we have also quickly seen that multiple trees are usually better predictors than a single tree. So the forest is usually better than a single tree. And I want to conclude this part with references that I used. If you're interested in this topic, going deeper is this book. I enjoyed reading it, and it's clearly written by James Witten-Asti and T.B. Shirani, An Introduction to Statistical Learning. I highly advise it. And then this other book here, it's nothing to do with machine learning, but it's a beautiful book on trees, the tallest trees in the world, and the stories behind them, and the people who go around the world trying to find, to spot, and to climb the tallest trees in the world. It's a beautiful read, which inspired this this lecture on my side. And I would like now to take a 5 minutes break. And then we'll reconvene, say, at 7 o'clock for a short demo on decision trees. So I'll see you at 7. Thank you. Let's take a break.
Hey everyone, just wanted to jump really quick. How has it been, the first part of the webinar? How are you finding it? Let's give Paula a moment. I'm trying to disconnect, but let me know if you're following, if you're understanding, etc. I've left some questions in the poll section, so just regarding us to see if this was the first time learning about machine learning, you have attended previous webinars, and if you have some experience in the data world. And yeah, I see that a lot of people are asking about the recording of the webinar. This will be automatically sent to you after the webinar ends. So if you have registered, which I believe you have if you're here, you will receive the recording in your email automatically. You can also check the recording by accessing the same link that you are right now, but after we've finished. So no worries about that. Paolo, I see your comment, but I see that you're still on screen, just like that you're like minimized to the left. So I cannot let you in again because it appears like you're still in here. Do you see here like really, really little like to the left? I don't know if you see it, but there's like an icon and it should be you. So, yep. Sorry.
Back in the program. Thank you. Yes. So welcome back, everyone. Sorry, I'm a couple of minutes late. Yes. Now I would like to give you just a short demo on decision trees, is just to give you a feeling of what they can do. Let me share my screen again. Let's see. Can you see my screen?
Nope, not yet. But we'll wait for it.
There's always a delay.
Still nothing, Paolo, but do you get the message from broadcast?
No, it's still processing.
Okay, well, maybe it's that. So okay, yeah, now it is up. I see it. Yep.
Yes, can you see it?
Yep.
Okay, great. Okay, so now as you can see here, this is, I don't know if you have any experience with it. This is a Jupyter notebook or Jupyter lab. And this is the environment that we'll use often in the course, in the data analytics course. And I don't mean here to get into details on the working of this tool. But it's very practical because it helps us to tell a story and to show some effects, to show some working of some algorithms, and to in essence to do data analysis and to share with other people who also use Jupyter Notebook and Jupyter Lab. In this demo, I would like to give you a flavor of how we can employ decision trees on a data set, on a real data set. And you will see that the training part, for example, is quite easy. Now let me start. So the goal here is to use a decision tree classifier as a weather forecaster. So we'll use a data set that contains data about the weather in Australia and train the algorithm to become a good weather forecaster for the day after. So knowing what the conditions are today, we would like to know whether it's going to be rainy or not tomorrow. This is the full data set that I imported from Kaggle. Kaggle is a platform where you can collect a lot of data from different sources, different types. This is weather in Australia. Here I do some manipulation on the data. I clean it a little bit. This is also an operation that you end up doing quite a lot as a data analyst, cleaning and replacing data and removing data which are not reliable, outliers, and so forth. Here I just do something very very coarse, because data cleaning here is not the goal, but decision trees is the goal. Here I restrict the algorithm. I use only some of the features. You see the original features are quite are several features. You have the location, the minimum temperature, the maximum temperature, the rainfall, the date, the sunshine, the humidity at 9 a.m., the humidity at 3 p.m. And based on all this data, whether it was rainy today or not, we would like to predict the rain tomorrow, yes or no. And going back to our previous discussion, these are all the features or variables. And rain tomorrow is the response or the target variable. This is the variable that we want to predict, the quantity that we want to predict. Oh yes, thank you, Erin. And this is Python. I'm using Python, which is also the language that is being used in the course most of the time. So here I restrict the data set to a smaller number of features to make the illustration concepts easier. Then I do some extra manipulation to balance it a little bit, because there were a lot of no and not so many yes. And if you have a data set which is highly imbalanced, like you see here, we had a lot of no's, 43,000, and not so many yes with respect to the no's. Then the algorithm might not work as well. So here also, this is not very important, but I'm just trying to explain a little bit, not in details, the steps here. So I'm cleaning, I'm balancing the data set. Here I'm showing part of the data set that I created after I've restricted it, after I balanced it. These are the features that we're using: the minimum temperature, the maximum temperature, the rainfall, the evaporation, to predict whether it's going to be rainy or not tomorrow. And you see, after balancing now, it's more balanced. We have 13,000 no's and 12,000 yes. So here, this is the main part. This is where we split the data set into a training part and a test part, as we've seen in the presentation earlier on. And this is the algorithm part. So here I'm loading the decision tree classifier, and I'm asking it to fit the decision tree classifier on the training set. This is in 2 lines. And the library, the Python library, takes care of the training. So you don't need to program the algorithm yourself. So the flowchart, the questions, yes and no questions, selecting the features, asking which of the features and which of the splits creates order in the data set, but it is all done automatically in these 2 lines. So, and this is often the case when we are doing data analysis or machine learning. The algorithm part is, so training the data is not the most time-consuming part. The most time-consuming part is getting the data, cleaning the data, finding the right algorithm, but running the algorithm on the data usually is not the most, it's not where most of your time goes. But this is something that I find very useful. So here at this step, we create the tree, and we're fitting the tree. We are creating the tree with, we are creating the model. So the algorithm, we are training the algorithm on the training data, creating essentially the model that then will be tested in the test phase. And there is a library that allows you to plot the tree. You see here, it will tell you that the most important feature is rainfall. Then if rainfall is less than 0.35, then max temperature, you have to look at max temperature. If it's less than 22.85, then you look at minimum temperature. And if it's less than 8.65, then yes, it will be rainy tomorrow. And there's the same reasoning for the other branches. So Python gives you also the possibility to plot a tree. The only thing, mind that if the tree is very deep, here I asked the algorithm to produce a shallow tree, so only 3 nodes. You can see here I restricted it by hand, so the plot is quite clear. But if you don't select a max depth of the tree, or you select a high depth, then the plot that you'll have here will not be readable. Will be very complex to read, because they will be very deep, many nodes, and the plot will be more difficult to be rendered. But nevertheless, this serves the example of showing how in Python you can plot a tree and train a decision tree. Here we can also visualize the performance of the performance of the model created on the training data itself using this table. And you'll see that it predicted correctly 68% of the data. So the combination of these values on the diagonal. So this is the predicted label and this is the true label, meaning that predicted no. So predicted no and the true label was no 32% of the time correctly. But there are times where it predicted no, but the true label was yes. So it predicted that it was not raining, while actually it was going to be raining. And we know that because we have the labels in the training phase. So also, you see, in this case, on the training data, the created model is not performing very well, because it's being successful only 60%, 68% of the time, but here it's not predicting accurately on this right diagonal of the square. And in the same way, we can then visualize the performance on the test data, which in this case is similar to the performance on the training set. So you see bad performance on the training data. In this case, you have a comparable bad performance on the test data. You have a performance of 69%, accuracy 69%, while here on the training set we had a accuracy of 68%, so equally bad. And this concludes this demo. Actually, I wanted just to quickly give you a flavor of how this algorithm can be trained, can be shown, can be tested with a real data set. So concluding, we showed how a simple tree can be visualized along with its performance on the training and test set. We mentioned how a tree that fits the training data very well can lead towards performance on the test set. So here, I haven't showed it here, and I will not do it right now. But if I, for example, because it will take some time to the algorithm to do it. So if I select a very deep tree, so for example 30 or 35 nodes deep, you will see that the performance on the training data will be perfect. Let's see if it works. Let me see. Let me increase now the performance, the max depth, for example, to 20, meaning that the tree is very deep. Now, I see. I have to run it from the top. Let's try it. It's a bit slow. But okay, I don't want to. No, it's did it now. Let me load it. Now I'm running the notebook from top to bottom to make sure that all the steps are run in sequence. Testing. And now I'm running it. Now it's running. Max depth 20. I want to do even more tree. Max depth 30. I will not plot the tree because it will take time to visualize it, and it will not be pretty, believe me. But let's watch now the performance with a very deep tree on the training data. You see now it's almost perfect performance on the training set. You see 51 and 49 all together, almost 100% performance with a very deep tree, meaning, as we saw in the example, that now the algorithm is confined almost every single data point it's in its own region. So the classification is perfect. It's sectioning the space perfectly. But now let's see what happens on the test data. So new data that have not been used by the algorithm to make the model. So we're testing the performance of the model with this very deep algorithm, and you see how it fails miserably. It was very good on the training data, almost perfect, but we have this error here of 40% combined on when it predicts no, where it actually was yes, it was rainy, or predicted yes, where actually it was not gonna rain. So combined 40%. So here to show you, that it can happen if you don't pay attention, and don't let that fool you, that a perfect performance on training set leads to bad performance on the test set. And now I want to leave you with a challenge. So trying to use a random forest algorithm, which I just touched upon during the presentation, to improve the performance of a single tree. So instead of using a decision tree classifier, you should try a random forest classifier in the step that we saw above. And that concludes actually my presentation, my webinar. I hope you enjoyed it, and that that increased your curiosity or tickled your curiosity on data analysis, data machine learning, and what you can do with the algorithms, and in this case with trees in particular. And if you have questions, we still have a few minutes.
Paolo, one of the questions came in, says, what was the test data in the example? Was it also the weather in Australia from the same source?
In the example, in the presentation. In the demo, you mean?
I'm not sure. Zinnia, can you elaborate on that a little bit?
So in the presentation, they were not real data. It's something that I made up to explain the steps of the algorithm. So this one that I show in the demo is real data taken from a real source. So here is the algorithm is really running on on true data, on real data. Well, in the examples that I gave during the presentation, I made it up to help me explain the inner workings of the algorithm.
Okay, so Zinnia has said, in the demo, was the test data really different from the training data?
It was. I'm still sharing, yes. Yes, so in this step, this is also quite simple that you can do it in Python. Automatically, this function splits the entire data set in two parts, the training part and the test part. Here you're telling him, give me 20% of the data, keep 20% of the data for the test part, and then leave the rest for training. And you see here, I'm creating the model using the algorithm on the training data, or 90% of the data. And then when I calculate the performance, I'm calculating the performance again on training here in this step. And when I calculate performance on test data, I'm calculating the performance on test data that the algorithm has not seen. So the model has not been created using this data.
Paula, I think David says in the chat, so to summarize, when we need more trees, it's better to use a random forest than a decision tree?
Sorry, Paula, can you repeat the question?
Yeah. So to summarize, when we need more trees, it's better to use a random forest than a decision tree?
I would say that usually a random forest performs better than a single tree. So if you want to have if your focus is performance, then by all means, usually the random forest outperforms the single tree. If you want to, if you're not interested too much in performance, you're happy with a lower performance, but what really counts for you is interpretability, then go for the single tree, because this is what you can show, on a single chart to your manager. This is how the algorithm makes the decision. Okay, if the amount is less than $50 and all these conditions are very clear, so explainability is very high. So if that is your goal, the tree is your friend. Otherwise, I would go for the random forest. If there is no much difference in performance between random forest and the single tree, and this you can test, maybe a tree is a better option because it has good performance in that case and good interpretability. But if your goal is absolute top performance, then usually random forest is a killer.
How do you determine the depth of a decision tree? Is there a rule of thumb or just by trying?
That's a very good question. I would say you try. I usually try and then check the difference in performance between training and test. So if I see that there is a lot of difference in performance between train and test, it means that I'm going towards overfitting. So then I decrease the depth. The more depth, the more deeper you go with the trees, the more with a single tree, the more you're risking overfitting. But you can catch it by comparing the performance of the algorithm on training set, on the training data and on the test data. If you see a big difference, meaning that very good performance on training, but test data is not good, as in this case, I would then decrease the depth of the training.
Okay. Well, I think we've answered every question. I don't know if you want to ask anything else. Take advantage of Paolo and Erin here. Otherwise, thank you everyone for coming today. I hope you learned a lot, you have some fun. And I believe you can agree, or you can add Erin and Paolo on LinkedIn. Maybe can you put this in the chat? And if you have any questions, maybe you can reach out to them about anything we talked today. You can also add me in LinkedIn, but I'm not going to be able to answer to your data analytics specific questions. But if you want to ask me about Ironhack, you can reach out to. Okay. Then thank you everyone for coming today, and hope you have a good rest of the week and a good weekend. Thank you, Paolo and Erin, for being with me today.
Thank you very much. Thank you, Erin. Thank you, Paolo, for hosting this event.
Yep.
They gave me opportunity to learn so much more myself about trees and and what goes around it. So it was a pleasure for me to share this knowledge with prospective students or people who are interested in answering their questions. Great,
thank you. Also expect to receive the recording in your email, as well as anything related to the webinar. Okay. Thank you. Bye. Have a good day.
Have a good day. Have a good evening. Have a good night.